Hello everyone, my name is Jim, and today I'll be presenting our work Goldilocks, Consistent Crowdsourced Scalar Annotations with Relative Uncertainty. This work was done jointly with support from my advisors Amy Zhang and Weld. Human ratings of items has become increasingly crucial in the modern day, from judging credibility of content to evaluating the quality of generative machine learning models, from understanding how toxic an online comment is to judging the quality of a product or service. We increasingly depend on scalar ratings to understand relationships between items. However, the way we collect scalar ratings today can result in challenges and problems for downstream applications, especially when the raters are somewhat uncertain about the property they're being asked to rate. One efficient and common way of acquiring these ratings is by asking annotators to place items onto a scale. This can be a continuous scale or a discrete bin scale like Likert or semantic scale. With a few annotators, we can derive an aggregated rating, and with enough annotators, we can even form a distribution over the possible ratings of an item. However, this simple approach can create a couple of problems. The first arises from the inconsistent interpretation of an abstract scale, as illustrated in this comic strip. Without shared concrete references to anchor against, different annotators may end up with rating values that disagree even when they would otherwise agree on the relative relationships between items. In fact, the same annotator can also produce inconsistent ratings with themselves as they refine their mental model of the scale after observing more items. Another issue arises from imposing precision on ratings. As prior work has shown, the ability to precisely measure items' ratings can actually vary depending on the item. A single annotator might find multiple placements equally reasonable, but are often forced to settle on one. This means item-level ambiguities can end up being incorporated into disagreement measures, reducing the actual informativeness about disagreement. To avoid the drawbacks of scalar ratings, one may decide to turn to pairwise comparisons, and indeed pairwise comparisons can provide several benefits here. Comparisons are more consistent since concrete instances are used, and disagreement between annotators really reflect true disagreements. However, pairwise comparisons can come with their own trade-offs. For one, comparisons increase the amount of work that needs to be done, and while approaches like binary search can improve this, the presence of ambiguity, or items that can't be compared, can reduce their effectiveness. Finally, while comparisons are great for understanding local relationships, they can often struggle to capture bigger picture global concepts, such as the magnitude of differences between items. Which brings us to the problem we set out to tackle with Goldilocks. Can we design a better way to collect annotations that combines the simplicity and efficiency of scalar ratings with the consistency benefits and the ability to better understand disagreement offered by pairwise comparisons? Our solution is range-based scalar annotation via Goldilocks. Now, directly asking an annotator to provide a range can be hard. Rather than a single value, an annotator now has to juggle placing two values. So to solve this problem, Goldilocks uses a two-step bounding process to discover the lower and upper bounds separately, reminiscent of that in the Goldilocks and the Three Bears story. First, we help the annotator find the lower bound by excluding all items they can confidently determine to rate below the current items, the too cold items. Then we switch to the upper bound by excluding the items that rate above the current item, or the too hot items. By using this two-step approach, we can create a range that's intuitively just right, without the annotator having to think too much about the range itself. Of course, in order to find these bounds, the annotator will need to compare against other items, and Goldilocks assists this process by using anchor items to ground the scale. Specifically, two types of anchors are used. Global anchors, a small set of items placed under the scale to allow for quick coarse navigation over a large scale, and local comparison anchors, which allow annotators to fine-tune their bounds by surfacing the immediate neighborhood around the current value. Additionally, once an item is annotated, it's placed alongside existing anchors, allowing annotators to reference their own past annotations in the future. Together, this allows us to use simple scalar rating interactions, while also providing the expressivity to separately capture ambiguity, or precisely how an item can be placed, and disagreement between annotators. We conducted several experiments to separately evaluate these designs of Goldilocks. Specifically, we wanted to answer two questions. Does using examples and comparisons improve consistency with scalar rating? And do ranges actually capture relative relationships between items better. Now, for these experiments, we selected 3 tasks where the rated items themselves are somewhat ambiguous, along with also having the potential for disagreement between annotators. The first is a comment toxicity task, which asks annotators to rate the intensity of toxicity present in online comments. The next is a food satiety task, which asks annotators to evaluate how filling or satiating it would be to consume the food depicted in the image. Finally is the age estimation task, which asks annotators to estimate the age of the subjects depicted in the photos. Now let's look at the first question. To evaluate the effect of comparisons on consistency, we created a single value continuous rating annotation task, where annotators recruited from Amazon Mechanical Turk were asked to place items on the continuous scale. We varied the way the annotators were expected to ground the scale, with one condition using only abstract text anchors commonly used in semantic or Likert scales, and the other using only anchors based on concrete items. We found that for the task domains that depended on subjective scales, in this case the toxicity and satiety tasks, examples improved interworker rating consistency. However, we also found that on tasks that are based more objectively, such as estimating an exact age, only using the examples can hurt consistency. This informed the final design in Goldilocks, where examples and descriptive anchors are both made available to annotators. We then evaluated whether incorporating past examples back into the scale as anchors improves a worker's self-consistency over time. This was done by varying whether such items are included, and evaluating consistency using a probe instance that was re-annotated at various time points. We found that self-consistency improved in both conditions, and while items that had high initial self-consistency tended to improve more when past annotations were included as anchors, we did not find sufficient evidence that the inclusions affected self-consistency over all probe items. Finally, we looked at the question of whether ranges can accurately capture relationships between items. Using direct pairwise comparisons between items as ground truth, we compare the level of disagreement over relationships as a distribution for each pair of items by deriving them from either range-based annotations produced by a full Goldilocks annotation process, and two other approaches that only made use of single-value scalar annotations. And we found that out of the 3, the distributions derived from Goldilocks ranges matched closest to those from direct pairwise comparisons. Finally, we'll discuss a couple of additional aspects of Goldilocks. One such aspect is addressing the cold start problem, or how to provide the first set of anchors when there aren't any ratings yet. In some cases, a requester may decide to create gold anchor examples to define the scale for the task, and we use this approach for the age task where the ground truth age values were available. However, when gold anchors are not available or desirable, we also presented one possible cold start seeding process, based on first creating a relatively diverse seed set through sampling and rejecting items from the dataset, followed by a single value rating to annotate all these items. We used this cold start process to create the initial anchors for the satiety and toxicity tasks, though alternative methods for cold starting may also exist. Finally, we note that while Goldilocks provides richer information, it does come with limitations. For example, range-based annotations can have higher cost to collect, which can limit the ability to collect larger datasets. Also, the current interface does not yet support tasks with long content, such as paragraphs of text, or cases that depend on context, like translations. Approaches for aggregation and iterative improvement of ranges also remains to be explored. In conclusion, we present our work Goldilocks, a novel technique to elicit scalar ratings while more consistently capturing and separating item-level ambiguity and disagreement between annotators. Thank you.